So in today's video, we'll look more closely at the net change theorem, and we'll look at the idea of our integrals within position, velocity, acceleration problems. So remember, our second fundamental theorem of calculus, the one we'll use most often, says your integral is equal to the antiderivative at b minus the antiderivative at a. This means that f prime would be the derivative of lowercase f. Another way you could write it is lowercase f of x is really just uppercase f prime of x. So really you're taking like the antiderivative of the derivative function to give you the original. And why this is helpful to think of it is because, remember, we know our derivative f prime, or in this case capital F prime, represents the rate of change over time. Because your original function could increase, then decrease, and then increase again, or think of it as if you're walking, you could walk forward, walk backwards a little bit, and then walk forward some again. Your f of b minus f of a only represents the net change. So for example, if you walk 5 meters to the right and then 4 meters back to the left, your net change would just be 1 meter to the right. Therefore, our integral itself doesn't account for all of the movement, just where you end up. So really, we could rephrase the integral as saying the rate that it's the net change. Because it's just the net change, there might be cases where you might want to see how far something actually traveled, and we will see that in this video. So some ways you can think of it is if capital V of t was a volume of water in a reservoir, then your derivative, capital V prime of t, is the rate at which the water flows. So if you took the integral of that rate, that would be the net change in the amount of water from time 1 to time 2. If v of t is your velocity of some object, meaning s of t is your position of some object, your integral of the velocity would give you the net change in the position, or sometimes we use the word displacement of the object over our time period. If we want to know the distance it traveled, though, we've got to look at separately the times. You can think of it when it was going forward or when it was going in reverse. You can find the time as going forward. You can find the time it's going in reverse, which will come back as a negative number. Take the absolute value of that negative number and combine them, and that'll give you the overall distance traveled. And we will see an example of that. So what this is saying is the absolute value of your derivative function. If you look at that graph, then take the area under the curve, that'll give you your total distance you traveled. And it's helpful to just see it with a visual. So if we have this visual, we know above the graph will be positive distance, or you can think of it as, say, traveling to the right. And the part below is negative distance, and think of that as traveling to the left. Well, if you just added those with the positives and negatives, it would give you your net change, where you end up, or your displacement. However, if you look at the absolute value graph of this, the absolute value graph makes any negative parts positive, so it would look something like this. So really what you would be doing, A2 would now be up here, really you'd be adding each of those sections. So how we can do this actually in a problem is we can split up the parts where it's above the graph and below, or above the x-axis and below the x-axis. The part that's below the x-axis, we can just add on the positive version of it. Like you notice here, we had negative minus A2. We just added on the positive version of that, and that can tell you the total distance that you traveled. And one other way to think of it, so say you went 5 this way, and you went 4 back that way. Well, our 5 in our integral would show up as a positive 5. The 4 would show up as a negative 4. But we just think of it as a 4 and say, okay, we traveled 9 altogether. if we think of acceleration, we know acceleration is the derivative of our velocity. So if you do the integral of your acceleration, that's telling you the net change in your velocity over a time interval. So the one example we're going to look at today is two parts. We're going to take this velocity function, t squared minus t minus 6 in meters per second, and we're going to find first the displacement. So that's just seeing the net change. And then we're going to find the actual distance that we traveled. There we'll have to take into account the absolute values. So we'll start out, we'll call this part A, the displacement. So in part A, we're just doing our regular integral. They wanted us to go from 1 to 4 of t squared minus t minus 6, and we'll have a dt. So we'll take our antiderivative. We'll have t to the third. We'll need a 1/3 out front. We'll have a t squared. We'll need a minus 1/2 out front. And we'll have minus 6t. And we'll evaluate that from 1 to 4. So we'll plug in our 4. We'll have 1/3 times 4 cubed minus 1/2 times 4 squared minus 6 times 4 minus parenthesis, because we have more than one term, 1/3 times 1 cubed minus 1/2 times 1 squared minus 6 times 1. And we'll evaluate this. 4 to the third is 64 times a third is 64 thirds. 4 squared is 16 times a half, so we'll have negative 8. And 4 times negative 6 is negative 24. Distributing our negative and simplifying the second part, we'll get negative 1/3 plus 1/2 plus 6. The 64 thirds and the minus 1/3 will give us 63 thirds, which is really just 21. So we really have 21. This will give us a minus 32. And then we'll have a plus 6.5 onto that. Combine your positives, you'll have 27.5 minus 32. 27.5 minus 32 will give you minus 4.5, and we were dealing with meters. Or you could say it as we went 4.5 meters to the left. And what that is that's our net change. So we might have gone back and forth, left and right a little bit, but in the end, we ended up 4.5 meters left of where we started. For part B, we want to see the overall distance traveled. Well, let's think about what our graph looks like. We've got t squared minus t minus 6. That can be factored into t minus 3 and t plus 2, meaning we should have roots at t equals 3 and t equals negative 2. So we have roots here and here. Because it has a positive squared value, that means we're opening up. So our graph is going to look something like this. Well, our interval is only from 1 to 4. So let's toss 4 on here. So we want to look just from here to here. Well, in that interval, we have a section that is below the x-axis and a section that is above the x-axis. What we need to do is we need to calculate those areas separately, and the area that's negative, we'll have to take the absolute value of it. Then we'll add them together, and that'll give us the total distance traveled. So we're going to do two separate integrals. We'll do the integral from 1 to 3, because that's where it's negative, and we'll do the integral from 3 to 4. And for both, we'll have our function t squared minus t minus 6 dt. So over on the left, again, if we're doing this correctly, that part should come back negative because it's below the graph. we'll have, just like we had before, 1/3 t to the third minus 1/2 t squared minus 6t, evaluated from 1 to 3. So that's 1/3 times 3 to the third minus 1/2 times 3 squared minus 6 times 3 minus 1/3 times 1 to the third minus 1/2 times 1 squared minus 6 times 1. Three to the third's 27. 27 over 3 will give us 9. 3 squared is 9 times the negative half will give us negative 4.5. And then we'll have a negative 18. Distribute your negative, you get negative 1/3. We'll get a plus 1/2. And we'll get a minus, or a plus 6. Well, the negative 4.5 and the half will give us negative 4. And the 9 and the negative 18 will give us negative 9. So we'll have negative 9 minus 4 plus 6, and then we'll have the minus 1/3. Negative 9 and negative 4 is negative 13. Plus 6 will give us negative 7. So we'll have negative 7 minus 1/3 to give us negative 7 1/3. Remember, though, we want the positive value of that, so we'll work with 7 1/3. That is the distance we traveled. It just happened to be to the left. That's why it's negative. We'll carry down our other one. Our antiderivative is the same. We'll have 1/3 t to the third minus 1/2 t squared minus 6t, this time from 3 to 4. So we'll have 1/3 times 4 to the third minus 1/2 times 4 squared minus 6 times 4 minus the whole quantity of 1/3 3 to the third minus 1/2 3 squared minus 6 times 3. And all these values we've seen before in parts of this problem. We have 64 over 3. We have a minus 8, a minus 24. And the parts from our previous problem, just the signs will be switched. We'll have a negative 9, a positive 4.5, and a positive 18. Well, these will give us negative 32. These two will give us positive 9. And we still have the 4.5 and the 64 thirds. If we combine these three, that's 13.5 and negative 32, which should give us 18.5, or in other words, that's 37 over 2. And that's negative, by the way, because the negative 32 controlled the value of that. And if we get a common denominator, we'll multiply this one by 2. We'll multiply this one by 3. We'll get 128 over 6 minus 111 over 6, which in the end will give us 17/6. So we have 7 1/3. 17/6 is the same as saying 2 5/6. So if we have 7 1/3 plus 2 5/6, that'll be 7 2/6 plus 2 5/6, which is 9 7/6, which in other words is 10 1/6. And that was meters was our units, and that is the actual distance we traveled So in reality, what we did is we first walked 7 1/3 meters to the left. Then we walked back 2 5/6 meters to the right. In the end, we saw in the first part that we ended up 4.5 meters to the left. That's it for today's video. We'll see you next class period.